Hi, welcome to my talk, Predicting Space Weather with Docker. My name is Chris Lauer. I'm a senior application developer at the NOAA Space Weather Prediction Center in Boulder, Colorado. We're also part of the Weather Service. It's an interesting organization. We'll talk about that here in a minute. But my talk today is in three parts. The first part is our early adoption steps, how we started using Docker, which might be of interest to some of you. The second part is starting to use Docker for real, how we started to move Docker into processing some of our critical data flows. And part three is how we started teaching our scientists to use Docker and collaborating in containers with the scientists we have on staff. So that should be interesting. So first, a little bit about the Space Weather Prediction Center. We're part of the federal government. So we're embedded in several layers of agency bureaucracy. I think there's 5 there. We have a different subject area than our parent agencies. It's not traditional terrestrial hit you in the face weather. It's space weather. We'll talk about that in a minute. And that means we have our own software section. So we have about 12 people in that section. And at any given time, the team size ranges from 6 to 10. We also have a couple. We have one Linux admin who's in a separate section, and one Windows admin or 2 Windows admins. So that's kind of the makeup of our tech staff. In case you're wondering, this is a small team. We have a FISMA high security system. We're a national critical system, which means we're not really allowed to go down, and we're not allowed to get hacked. So our parent agency said no cloud. We're not ready for that yet. That's getting a little crazy. Let's stay on-prem and safe and secure. So that's kind of meant we had to build all this stuff on premise, which means we did this a little differently than a lot of people. And one more thing I should mention is we have a really cool mission, and that's one of the great things about working in the government is that you often have a really cool and important mission that people feel really passionate about, and that can give you a lot of energy to do things right, to do things well, and to care about your customers. All right, so what's space weather? Space weather encompasses pretty much everything that's going on in the 93 million miles between the Earth and the Sun. So that's a few different kinds of phenomenon. So you have electromagnetic radiation like X-rays, from X-ray flares that can impact communications and humans in space. You have energetic charged particles that come from flares and coronal mass ejections that can impact satellites and high-frequency communications, especially near the poles. So it's protons and electrons flying out of the sun really fast and hitting us. And magnetic field impacts. So coronal mass ejections, you can get magnetized plasma that interacts with the Earth's magnetic field and causes some beautiful auroras, but also can impact the power grid in some fairly negative ways. And pipelines and other ground-based infrastructure. So pretty interesting stuff where we're just looking at the sun and trying to figure out what's going to happen to us here at Earth. That's space weather. So a little bit of background on our culture. We moved to Agile, which is a little bit rare in the federal government. And we started that move back in 2012. So we trained our developers in Scrum. And that really taught us how to build a consensus on our team and then inside the organization, which has been super important. And then we started sprinting for about 8 years, off and on with different team sizes and different team formations and, changing and evolving and adapting as we go. But if you go back to the Agile Manifesto, one of the values I really care about is customer collaboration over contract negotiation. So instead of doing the federal government thing where it's like, give me 100 requirements that all have the word shall in it, we're just going to build the best thing we can and iterate on that and really trust our customers. So after doing this for 8 years, we saw some pretty big improvements in morale and some pretty big improvements in capability to deliver. But it was still time. It was time to improve our technical tooling for delivery. So let's talk a little bit about that. So here was our architectural challenge. How do you get started with continuous integration with this? And by continuous integration, I mean you check in some code, it gets built, and you're able to do a bunch of testing automatically, end to end with every single commit. So what we had was a giant single Microsoft SQL Server database of all things for all of our data. And this meant, this is space weather. We have ground-based data. We have several satellites that feed us data. You've got forecaster generated data, forecast, observations, all mixed together. And then we have all these applications that all hit the database directly. So there's no service layer. There's deep coupling. Everything has its own MS SQL driver to connect back to MS SQL. And you've probably got some views or stored procedures. So there's some abstraction there. But you're combining all these disparate data sets into one thing for your applications. You've got all this business logic in the database. So whenever you tried to do a build and test against production data, that was very challenging, because you've got this giant thing that's got all these interdependencies that are very difficult to understand. That if you wanted to try to improve the database, databases are notoriously hard to version control. So this was really a sticking point. So how do we get started? This is part one that I alluded to earlier. We're going to seek out a new way. And how do we do that? So back in August of 2017, we took some Jenkins and continuous integration training, because we'd heard about this continuous integration thing, and we just couldn't figure out how to do it. So we had Ryan Blunden, who I think is now out of SourceGraphs. Shout out to Ryan if he's listening. He came out and gave us some continuous integration training, and he delivered that with a Docker tool set. And a couple of our developers got really excited about that. This Docker stuff is cool. This is what we need. We could see how it's going to solve all of our problems. Then we labeled the old way. I think it's important to understand where you're at. And it's called shared database integration. And then we did some research on that. And Martin Fowler does not have a lot of good things to say about shared database integration. Then I read up on a new way, Building Microservices, a book by Sam Newman. Even if you're not going micro and you're just going service-oriented, really good book about the values of loose coupling and high cohesion that can help you build software. Domain-driven design is another concept that might be helpful as you're trying to figure out how to break down your legacy monolith. So then we found a small, high-value team project, and this is the verification service. So we're going to try to take some of those observations and some of the forecasts that are poorly stored in our database, and we're going to try to compare them to each other and say, how good is our forecast? But this wasn't going to be national critical, high security. It checked something important off the list that we were committed to that year. So we grabbed this one, and it would have been hard to do the old way. And then we split our too large team. At this time, we had a team of, I think it was 9. We split it into 6 people working the new way. We were just going to do the verification service completely separate from everything we'd done before. And then 3 to keep working on some big legacy database projects. So we had one team ready to go. And then that team adopted these some new rules to develop the verification service. So here's the new rules we used to drive this culture change. But actually, before that, why Docker? I mentioned we were really excited about that from that continuous integration training. Why were we so excited? One of the main things is the issues with scientific software. So scientific software often has delicate, conflicting, and just downright weird dependencies. Libraries you haven't really heard of. IDL is something we use a lot at Swipsy that actually requires a license at runtime. And then maybe you have a lot of dependencies at build that are different than dependencies from runtime. So, when you go to install these in a traditional system, you got to get it exactly right. And then if you upgrade this one, it breaks that one. So like you can have one that requires a certain version of matplotlib and another piece of code, maybe even in the same project, that requires a slightly higher version. So being able to figure that out was something we got really excited about. So we can encapsulate these dependencies. And actually, as we transfer things into Docker, in many cases, this is the first time the dependencies have been well documented. And it lets us iterate on figuring that out. Because if you miss one, you just add it to your Docker file and build again. Does that work? Okay, excellent. So that was really huge for us. Some of the software isn't really very configurable either, and maybe I'll mention some of this later. There, you can have hard-coded paths and lots of Fortran or IDL or Shell or Perl. It's not from a configuration file. But that's okay, because inside your Docker, you can have whatever paths you want. You just try to deal with the data persistence with bind mounts in your Docker Compose or whatever orchestrator you're using. So the inside of the container can be really weird, but the outside can still be really nice and tidy. And the other thing was easing deployments. And I mentioned CI before, but just being able to make sure that what you have in your own local development environment matches what's on staging and matches what's on production, and those are all going to work. Docker images and the tags on those really makes that easy. So I highly recommend it for that. And as long as we can solve how the data are persisted and how each piece of software is configured, then we've pretty much got it captured programmatically, and anyone on our team can look at that in version control and see exactly what's going on, which is kind of new for us. Big improvement in software quality and our ability to cross-train there. All right, so here's those new rules I was talking about, and there's 6 of them. So the first one, we've been doing shared database integration for so long, we made this new hard rule. Only one thing talks to a database, and in our case, it's the service. So if you want to post some data or you want to read some data, you're only allowed to talk to the service, and the service is the thing that has a database behind the scenes, and you don't know what database that is. So this was really hard for us. We kept drawing that line from services back to the database, even though we weren't using MS SQL anymore. So we had to really get serious about this rule. And we were going to go microservices. So that's a collection of loosely coupled, highly cohesive services. So figuring out how to break down a problem into these different services. That was a new thing for us. And we're going to design this with automated end-to-end testing in mind. So the goal is that Jenkins on each commit can stand up all the components, the back-end database, RabbitMQ, whatever, and all the things we've written, drop some data in, have it ingested, processed, posted, and then retrieved, and make sure that looks right. So this is going to be really cool. And it's going to be event-driven. Space weather moves at the speed of light. So it needs to be low latency. We still want that loose coupling, so we're going to use asynchronous messaging, publish, subscribe as an important new architectural feature. And we started to adopt 12-factor.net practices. So these became the new default for us, especially store configuration in the environment, from the code's perspective anyway, and log the standard out. So stop having each piece of code manage its own log files. Just blurb out what's going on, and the orchestrator will figure that out. And we're going to adopt a whole bunch of new stuff. So at this time, we went to NoSQL for a more developer-friendly database. And the nice thing about NoSQL is you don't have to version control your schema. You don't have to declare a schema up front. So as you discover the data, you don't have to worry about all that. As long as your code, and this is what we did, as long as your code makes sure the right indexes are in place, that's pretty much all you have to do. And we also adopted Python Flask and Python in general at this time. We kind of consolidated on that as a language, Python and JavaScript. And RabbitMQ for that asynchronous messaging. And that served us really well. And of course, because this is the fun part, and this is why this talk is here, Docker containers for everything. So how did it go? It was amazing. Developers were very happy. They were really excited to be learning all this new technology. And what was kind of funny there is that it wasn't any slower. So it was almost impossible to deliver in the old way. So it was just as fast, and maybe faster, to learn all this new stuff and deliver. So we got all this learning for free, basically. So the pace of learning was very rapid. This made iterative changes much easier. Everything's in a container. We can all run it on each other's machines. And it was just so much faster to learn all this stuff. And our customer was happy because we were able to deliver some modern capabilities, queryable service, and that's updates with low latency. And he was able to brag about this verification service compared to the ones that our international partners had that had been making him jealous for years. But, and there's always a but, the microservices team got way out ahead of the organization very quickly. So those people on the database team, how do we even begin to tell them how much fun we're having and how awesome this is and what this lets us do? And also the system administrators, they were pretty slammed, pretty busy with their old job. How do we teach them the new way? And we found we'd made a few mistakes, so we'll have some learning time here in a minute. And we also started hitting some new obstacles. It's not always easy. So we couldn't build our containers in our secure environment. There's a pretty obvious solution to that, and I'll get to that later. All right, some of those small lessons. So here's some small lessons from our early security mistakes. First off, don't give anything Docker daemon access. We made the mistake of monitoring our services with Nagios, which we'd always used. But by having it do a Docker PS or call onto the Docker API and see what's running, unfortunately, that meant it had Docker daemon access. So penetration testers came in, and Nagios wasn't very secure, and they were able to compromise the machine through privilege escalation, because they basically have root. If you have Docker daemon access, you basically have root. So don't give that to anything. With the caveat that if you do give it to something like Jenkins, because we had Jenkins trying to automate this pipeline, it needed Docker daemon access, the CI pipeline, lock it down. And we made the mistake of using Jenkins. We installed Jenkins, we went to CI training, we played with Docker a little bit over the holidays, and then we started this verification service almost a year later, and we didn't think to double check that our Jenkins was appropriately secure. So the pen testers were able to take advantage of our lax profile on Jenkins, which we fixed, so it's good. All right, so that was great. Let's move on to part 2. Let's keep learning this Docker stuff, and let's do it for real. Let's do it with a critical data source. So here's our data source, Ghost 16. So this is the next series of operational weather satellites that take beautiful pictures of hurricanes. They get a lot of data into terrestrial models for Earth weather. But they also have a space weather instrument package. So we got to replace this. We got to replace all of our legacy GOES from the previous series of GOES satellites with this new stuff from the new series of satellites, which is a little bit different. And GOES data is really important to us. So the satellite's out at 22,000 miles, and it's monitoring X-rays, which is one of our NOAA scales, which is kind of like a hurricane scale or a tornado scale, but for space weather. So it's monitoring X-rays, so X-ray flares, which can impact communications, among other things. And particle data as well. It monitors kind of what's going on with particles for other satellite health. And then there's also some component of high altitude radiation exposure that it's monitoring. So that's the other scale, is the high energy protons. And so this has to be low latency, and it has to be reliable, and we can't have a bunch of downtime when we're switching over from the old stuff to the new stuff. And because it's so critical to our mission, a lot of our legacy applications written in a variety of languages, Perl or MS SQL or PHP or Visual Basic, Microsoft Access, of all things, they talk directly to the database to get this GOES data. So this is going to be a bit of a challenge. We're going to do this without MS SQL. We got to touch everything. So here's how we did that. So we used Docker here in our new services to build a bit of a strangler pattern. So we built this service that could handle the data in a Docker, much the way we did the verification service. So it's going to hold on to all the GOES data. And that service needs to understand really two things. So it needs to know enough about the data, both from the old satellite and the new satellite, so it can store them in a comparable way. And then it needs to know how the applications use that data, so treating them as customers. And then it can solve all the problems that customers need solved. And then we're going to add the old data to the service. So that's the old GOES 14 and 15. We're getting 16 here, but first we've got to add 14 and 15 because that's what we're currently using, what's currently operational. And then we can port those legacy applications to use this service really one at a time. So you don't have to do them all and deploy them all on the same day. We're just going to deploy one at a time, switching it over from the MS SQL direct call to calling our service and getting some JSON. And we'll do that for each one in a variety of languages. And then we'll add in the news data as it becomes available. And once everything's ready, then we just change which one is primary, and all of our applications downstream automatically start getting data from the new satellite, and they don't even necessarily have to know that. It's great. You go live, no downtime, everything's seamless. We tried this a few times before without Docker, but this time it was even better. And just for kind of a picture, like if you're thinking about going microservices or Docker, this is a breakdown of how many containers it took. And there's actually a few more than this because I don't think I have the cleanup one in here. And I'm not going to go through all these, but of interest maybe is the LDM container here. So LDM is a piece of software that's used a lot in terrestrial weather in our parent organizations to send data, transmit data between partner organizations. It's Unidata software, and we thought, man, this is kind of complicated, and it's like 20 years old. How on earth are we going to containerize this? But on a fluke, we searched Docker Hub, and it turned out they'd had a container version of it, and it didn't quite work when we first tried it. But they were excited about this Docker stuff too, so we collaborated with them a bit, reached out to them, and we got to a point where it worked, and we were able to containerize this part too, which is super exciting because it made it much easier to deploy, and we understood the configuration a lot better. So that was really awesome. So always ask. All right, so now the new way of doing business is starting to solidify. We've discovered that using Docker Compose as our deployment, we have 2 hosts in production and 2 hosts on staging right now, maybe 3. We're all developing our own virtual machines on our Windows boxes, but Linux virtual machines. And then we're putting it on staging, making sure it works, and promoting it to production. But as we've solidified this new way, there's only 4 deployment artifacts. So this is why deployment is feeling really easy. We know exactly where to look. I'm going to go through those briefly. So first, your Docker Compose.yaml. If you're using Docker Compose, you're familiar with this. But this is this file defines the relationship between each service and the host. So that's the bread and butter one. And then there's a .env. So this is a little trickier because it hides on the file system. Because it's a dot file, but Docker Compose can read environment variables from this file. So this means that if our .env is different on each host, but Docker Compose uses environment variables, we can abstract those host differences, and the Docker Compose file can be the same on each host and in development, and the only thing that's different is the .env. So that's really nice. And then your service configuration environment files. So, all your configuration now is in files, but from your application's perspective, it's coming from environment variables. So if we get a more mature orchestrator eventually, or a more feature-rich one, we can use these environment variables there instead of in files. Be super cool. And then here's that problem before, how we couldn't build things in the secure environment. We solved that by adopting Harbor. And this took about an hour or 2 to install, and then another 6 hours or so to figure out what was going on with our certificates. But once we had it, this is our internally hosted on-premise registry. Once we had it, this became the really fun part of seeing our images. And this is what our Harbor looks like right now. So these are all the projects, and each project has several repositories, and each repository has several tags checked in. And this means for deployment, you just update the tag, build the image, update the tag, push it to Harbor, and then it can be pulled from anywhere at Swipsy and rolled back very easily to a previous tag. So I think this is a Cloud Native Computing Foundation incubating project. It's got a lot of good endorsements. Highly recommended if you're looking for an on-premise registry and having a hard time making a decision. Just try one. You need one. All right, so also part of that new pattern that was emerging, here's our deployment steps. Very easy to deploy now. So one thing I didn't mention is for each project, we make sure we have a UID for that project. So everything in the same Docker Compose might use 1 or 2 different UIDs, and that should map to an account on the target host. So the user inside the container maps to an account on the target host. That's partly a government thing. So make that account on the target host that has a matching UID, and then go to that account, set up a Docker Compose, set up a .env, and set up the environment files for each of your services. And then you can add a robot account in Harbor, so you can Docker log in with that. So you can pull images, and then you do a Docker Compose pull, and it'll go get all the images from your Docker Compose file. Docker Compose up-d to bring it up in the background, and Docker Compose logs-f to make sure it's working. And if it's working, you're done. That's it. And that's how we're going to deploy anything now. Pretty simple. We wrote this down and made onboarding really easy. It's pretty cool. All right, so now we're using it for goes. How did it goes? Excuse my terrible pun there. Again, it was amazing. It just works. The new technology we'd chosen, Python and RabbitMQ, or the low latency and the reliability, the ease of reading code and collaborating with each other. And then MongoDB, very high performance for what we were doing, just time series databases. We didn't have to throw away any data. We were able to build really cool capabilities. And here's the visualizer, which is hosting some JavaScript in a container and calling the service with queries for just the data it needs. Yeah, it was really awesome. Forecasters were happy with what we built. The public was pretty happy as well. And we're really proud of it. And here's, since GOES also provides imagery of the sun, we also did that part. So here's all the different channels of imagery that are available. That's also in a container in a different way from what we did before. You can query it and get a really long loop or interleave loop. Pretty cool stuff. We're having a great time. So I did promise a big mistake, and this is where we really got it wrong. We did not build continuous integration into our deployments or monitor it. So we kind of had this pipeline doing the end-to-end testing, but nobody was checking to make sure it actually worked. And we weren't very good at writing tests. It took a long time. And here you can see that one failed after 2 hours and 10 minutes. They're broken more often than the code. And because no one was checking, we didn't get an alert, or it didn't gum up the works if the test failed. Developers just stopped looking at it, and they got a bit frustrated with it. And so we still don't have a working pipeline for this one, for GOES, which is super important. So because developers ignored these failed builds, we didn't hook it up, we missed a big opportunity to deliver that continuous integration promise that was a big driver of why we adopted this architecture in the first place. All right, so this Docker stuff is great. Let's do it for everything. Really easy for dev, really easy for staging and production. Really easy to just work on the part that needs to be fixed. Great collaboration between devs and getting intentional about that data persistence. This is going well. We should really do it for everything. So let's talk about that. Suddenly we had a short fuse expansion of our mission. The International Civilian Aviation Organization, ICAO, tasked us with forecasts of different impacts of space weather on aviation. And that includes GPS error, high altitude radiation exposure, and communication outages. So in a few months, we had to deliver this capability. So we needed models, and we had models, but they were in varying states of definitely not ready. So moving on to part 3, collaborating with scientists to get these things ready using Docker. All right, so let's teach them Docker. So the first step was I gave a presentation to the scientists, Docker containers and continuous integration, where I talked about how awesome this new architectural pattern was, how great these new tools were. And then we tried 3 different ways of collaborating with the scientists, depending on who they were and what the models were, to get these models into production, something which they'd never been in production before, in containers using Docker and Docker Compose very quickly. And you're probably thinking it went kind of like this XKCD comic. And I'm not going to lie, there was a little bit of that, but it actually went pretty well. And let me talk about each one briefly. So CTIP-E, you're worried about the maximum usable frequency, communication outages. This model had been running for a long time in staging, but several of the developers were gone. It had Fortran code and hard-coded paths, but we were able to break this into several different Docker files for the model itself on a multi-stage build. So you're building that model and then you're putting it in the file, the Docker container, and then you're able to do all the scripting around it. And we were able to just kind of take it and get it working, get all its dependencies isolated, so it was portable for the first time, and new developers were able to stand it up very quickly. So that was really cool. Global total electron content was a little harder. In this case, we let the scientist that was working on this, he didn't really have time to collaborate with us. We didn't really have time to collaborate with him, so he kind of did it himself. And this was a little bit like the SKCD, and we had to come up and clean up a lot later to make it more reliable. But he was super excited to work on it, and where he left it, even though it was pretty messy, to be honest, it's a great starting point. The runtime dependencies were all captured, so that was really cool. And then Carry 7, this is where we really did it right, and here the scientists really took an interest in Docker. I think the reproducibility aspects were really exciting for them. So we worked closely with her. We helped architect it up front, and then when she had a problem, she'd come to us and we'd help her work through it. So we got something we're all proud of that works very reliably. It's even event-driven using RabbitMQ. Pretty cool. So let's move on to the benefits. We're having a great time using Docker. So we just got a new dev. We were able to onboard them in about a month and get them contributing just by teaching them Docker. It takes about 5 minutes to deploy to production, or it used to be an hour if we were lucky. A minute to roll back a deployment, another 5 to try again. So that's really simple. And about an hour to get your dev environment working, which used to be about a week. And here's our team. Thanks to the team. Shout out to everybody. Thanks everyone for listening to the end. Great time at DockerCon.